Hello everyone and welcome back to Advent of Code Day 7. Today's task is called Laboratories and it goes as follows. You thank the cephalopods for the help and exit the trash compactor, finding yourself in the familiar halls of a North Pole research wing. Based on the large sign that says Teleporter Hub, they seem to be researching teleportation. You can't help but try it for yourself and step onto the large yellow teleporter pad. Suddenly, you find yourself in an unfamiliar room. The room has no doors. The only way out is a teleporter. Unfortunately, the teleporter seems to be leaking magic smoke. Since this is a teleporter lab, there are lots of spare parts, manuals, and diagnostic equipment lying around. After connecting one of the diagnostic tools, it helpfully displays error code "Oh no," which apparently means that there's an issue with one of the tachyon manifolds. You quickly locate a diagram of the tachyon manifold, your puzzle input. A tachyon beam enters the manifold at a location marked S. Tachyon beams always move downward. Tachyon beams pass freely through empty space, which are marked by dots. However, if a tachyon beam encounters a splitter, which is marked by an caret, I believe, up caret, the beam is stopped. Instead, a new tachyon beam continues from the immediate left and from the immediate right of the splitter. For example, this is how our example input looks like. And our beam in this case is represented with a pipe sign. And when it reaches a splitter, it gets it creates a new path from the left and from the right of the splitter it has stumbled upon. Going along, and so on, we do that until we reach the end. To repair the teleporter, you first need to understand the beam splitting properties of the tachyon manifold. In this example, a tachyon beam is split a total of 21 times. Analyze your manifold diagram. How many times will the beam be split? So, to closely showcase how this whole task is supposed to look like, I created here with my drawing expertise a small diagram where we will be drawing beams that will showcase the path how it needs to be. So of course we start from the letter S, which is our starting position, and we get a beam starting from it. So let's say the beam just goes as following, or in this case it should be like this. And now it stumbles upon a splitter. Splitter splits the path into two possible ways. It splits it immediately to the left and immediately to the right. In this case, this beam will then get split like this and will then get split like this. So now we have two beams, and the task asks us how many times has the path been split. So in this case, it has been split once because it stumbled upon one splitter. And now for this last caret, this current new beam that we have stumbles upon another caret splitter, and then it again does it towards the left and towards the right, and that's another split which equals to 2 times the beam has been split, and this right side beam just continues as per usual. So understanding this task visually was very, very helpful because I managed to create some sort of a code inside my head that will make this easier. So I will explain the algorithm we'll be using for our part 1 using this visualization. So let me just remove this beam. So what we will first do is we will need to get a starting position. We know that we will of course convert this whole grid or tachyon manifold diagram into a 2D array where our rows will be, these rows, and then we will have each character corresponding to its own column. Once we have that, we will need to get our starting position. Our starting position, luckily, is always in the first row, which is gonna be on index 0, and is always in the center, which is gonna equal to the length of the row divided by 2. So we can maybe write that. In this case, we will use this example. So we'll have 0, 1, 2, 3, and 4. We know it's 4 divided by 2. So our starting position, gonna mark it as SS. We're actually gonna use text for that. SS starting or SP starting position. We'll have a row at index 0, and we'll be at 2. Or I can just write a length of first row divided by 2, floor division, if our row happens to be an odd number, which in this case it is because it has length of 5, so divided by floor division by 2 is 2, which would equal then to 0 to 2. Now once we have that, what we will do is we will check the following. We have our initial position, and our initial position is this S, and right now it's only 1 because our beam needs to start from somewhere. So we will be using these coordinates 0, 2 to start doing our path trajectory. So having this initial position, we will create a variable that will hold our new positions, and we can call it something like NP, which in our case will be a set of coordinates. Now, why is that? For example, let's say we have a beam that comes up twice, like for example, let me just mark it here. We have a beam coming here, and then these beams get split twice, and in this case then it would be like this, this, and this. These two splitters share this middle one, so we don't want to have duplicate coordinates. They all need to be unique, and in this case we can ignore that one. Once we have that, we will be populating these new positions set with the new beam paths that get created if we stumble upon a splitter. So in this case, we will be, of course, going through our initial position or initial positions, which we will do like for P in positions. And our positions is basically gonna, initially our positions is gonna be holding this starting position, and as we going, we will be holding the new positions that we have created. We'll basically be doing a recursive pass-through to get all of the valid, to get how many times our beam gets split. Now once we have that, we basically now just want to check. Since we know that all of the beams are synchronously coming down as we are going through, there was no in task an indication that it isn't like that, we can immediately, our breaking point will basically be either if I will just call it like we break, either if length of our positions equals 0, or if our current row position is equal to the length of our grid minus 1. So this is our break condition. So we can break after the recursion and we can return a result. Let's get back to here, and now let's just start. Now we will also like generate a new position by just incrementing the initial row plus 1 and R like new row. And once we have that, we will just check if in our grid on a new row and on our current column we have a caret, then what we will do is we will just add to a new position, dot add a tuple of our new coordinates. So we'll have an r, and we will do call plus one, and we will do just a second, whoops, nr call minus one. These two positions will correspond to the beam breaking. So we have something like this. This is the beam, and if we reach a caret, this is gonna be a new row and a column plus one, minus one in this case, and a new row and a column plus one. And once we have that, besides, if we cannot do anything, we will just do else. If we can't do anything, we will just add into a new position. I wrote this as NP, that's fine. New position dot add, and we will add our new row and a current same column. And then what we are left to do is we will return our function. I will just mark it with F. We'll return a function that will accept again the grid, so we can iterate through it. It will accept new positions, and that's basically it. And of course, current splitters, that how many splits we already have had. So let's start writing our code. As always, we will start off by opening our file, example as F. We will store our grid into a tachyon, or is it with an epsilon, tachyon manifold equals like this. And for line in F, in tachyon manifold, we will append our line, which we will of course convert into a list so we can get each individual characters, and we will strip the line so we don't have the new lines at the end of them. Now, to keep things nice and organized, we will create a function that will be called get starting position, which will accept a tachyon manifold, or a grid in this case. We start with a row 0. Our column will be equal to length of the tachyon manifold. To maybe make it dynamic, depending on how if each row has its own length, we will pass in a row in this case. Length tachyon manifold of the row, floor division by 2, and we will just return a tuple of row and column. So once we have that, we can do starting position equals get starting position of a tachyon manifold. And if we would check a starting position, we would see that we get 0 and 7, which corresponds to our example input, which would be 0, 1, 2, 3, 4, 5, 6, 7. Row 0, column number 7 in indices. Now we will start writing our function, our main function that will hold the logic for beam splitting. And we will call it, I'm just gonna call it part 1 because I'm extremely creative. We'll pass in our grid, manifold. We'll pass in the positions we are currently working with, and we will have how many total splits we had. We can give this a default of 0 because, well, we're starting with 0 splits. And so first of all, as we said, we had our two breaking conditions. If the length of our positions equals to 0, so we have nothing more to check, we return the total splits. We will create a new variable that will hold our current splits for this section. So we will, for this current cycle, and we will create a new positions set that will hold our positions that we get when the beam splits. Now we go for position in positions, and we can get a position row, position column from the same position. And now another break we had is to check if the current position row is equal to the length of the tachyon manifold minus 1. If so, we return total splits. Now we just update our we update our position row by putting it to a variable new position row is equal to a position row plus 1, since we want to go step by step. And now we just check if in our tachyon manifold with a new position row and a current position column we have a caret or a splitter. We, into new positions, we add a tuple of the new position row and a position column of minus 1, and let me just copy paste this so I'm faster, and a new position of plus 1, and we just do current splits plus equals 1. We also know that we have an else condition if nothing was met, if there are no splits, if this is just a simple dot for the current position, then we just add to new positions. We add our new position row, and we just leave the position column as it is. And now all that is left to do is to use these new positions as our argument, or as a new argument in our function. As we said, it will be a recursive. So we do part 1, we pass in again the tachyon manifold, we pass in the new positions, and we pass in current splits. Now that should be it. I will do total splits equals a part 1 of tachyon manifold, and we will pass in a starting position, which is gonna be a set, and in Python sets can be marked with the curly braces. We'll pass this starting position, and that should be it. Not part print. Let's check if this will work. Total splits. We do this, and we get 21 for the example, which is the correct answer. And if I would check it for mine, it's 1690, which is the correct answer. Now let's start off with part 2. With your analysis of the manifold complete, you begin fixing the teleporter. However, as you open the side of the teleporter to replace the broken manifold, you are surprised to discover that it isn't a classical tachyon manifold. It's a quantum tachyon manifold. With a quantum tachyon manifold, only a single tachyon particle is sent through the manifold. A tachyon particle takes both the left and right path of each splitter encountered. Since this is impossible, the manual recommends the many worlds interpretation of quantum tachyon splitting. Each time a particle reaches a splitter, it is actually time itself which splits. In one timeline, the particle went left, and in the other timeline, the particle went right. To fix the manifold, what you really need to know is the number of timelines active after a single particle completes all of its possible journeys through the manifold. In the example above, there are many timelines. For instance, there is the timeline where the particle always went left. So this one confused me at first, but I'll try to explain it through the Advent of Code website without actually showcasing the visualization, because there's a lot to showcase. So in this case, we don't have a sink of beams that we had before. Now we have a singular beam that Depending on the split, or depending on his splitter, we either take a left and then work with that value, or we either take a right and then we work with that value for each split we encounter. So in this case, they have provided an example where the particle, tachyon particle, always goes left. Here it makes a zigzag every time it makes every time it finds a caret, like a bit left, bit right, bit left, bit right, and so on and so on. Or it takes some arbitrary path. So basically, we need to simulate all possible timelines, as they call them, or journeys of our particle. So it can maybe all be all right. Maybe at the beginning it goes left, then it goes all right. Maybe it goes first two times left, then all right, and so on and so on. So let's start writing our part 2 solution. This part 2 really caught me off by surprise the first time I started, because I thought it would be much more difficult. So I guess that made it a bit more complex in my own mind. But it's actually surprisingly simpler, in my opinion at least, as we will see as we will be writing it. But one thing we can sort of conclude from the beginning is that traversing all possible combinations through a 2D array grid isn't very fast. So in Python, we will be utilizing a caching system in place. And in Python, that's pretty simple, because from functools, their library or module, how they call them, we can import a so-called LRU cache. It means least recently used cache, and this is a decorator that you add on top of a function, and it automatically caches your functions. So to quickly explain how LRU cache works, let's say we are trying to calculate a Fibonacci sequence for the first 10 numbers. We start off from a 0, of course, a sum of 0, and then for 1 we know that the Fibonacci sequence for the first number is 1, for the second is 2, for the third is 3, for the fourth is 5, for the sixth is 5 plus 3, which is 8, and so on and so on. And when we would have a Fibonacci function, we would have to constantly, again, recursively call our function to check. Okay, so like for example, we are checking for the 5th element, then we have to do Fibonacci calls for the 4th, 3rd, 2nd, and 1st element. But using LRU cache, we can cache or store the values of the previous Fibonacci sequences and just use the last one and add the new one on top of that. So in short and roughly explained, that's how it works. So now once we have that covered, we will be using that for our function to get all of possible timelines or journeys, however you want to call them. And we can start by creating a function that is called we will call it part 2. We will tachyon manifold, and we will accept a position. We will accept the position. Now we won't be accepting positions. We will be accepting a position because, as we will see later, this will be this is what I was talking about. It's a bit simpler than this one. And now what I will do, since LRU cache needs to work with a hashable values. List isn't hashable, but we can turn our grid into a list of tuples, which are hashable as tuple. I'm just gonna write it like this, and for each row uh, for row in our Tachyon manifold, we will convert it to a tuple. And now we have a tuple of tuples, and we will create a new function, definition, get all timelines, I guess. And this will accept a Tachyon manifold and the position. And this is the function that will be caching. And to do that, we just do @LRU cache, and that's it. And here we will return the get all timelines. We will pass a Tachyon manifold as tuple and the current position. So let's start writing our function. We will pull out our current position, into two variables called current position row and current position column, which will be a position. And our breaking point for this one will be if we have reached the last row. If a current position row equals to the length of Tachyon manifold minus 1, we return 1, because we will be only adding one journey when we reach the end, because we know it's for only one particle. We will get a new position row, which will just be current position row plus 1. And now we will also have a small check. If our new position row is bigger or equal to the length of this Tachyon manifold, so we don't have any index out of range errors, we will just return a 0. We can return a 0 because we are not adding anything with it, so it works. Now we will hold a variable called possible timelines, my bad. We'll have a variable possible timelines that will hold all of our timelines that the beam has passed so far. So we can do the following. We can check again if at our Tachyon manifold on a new position row and a current position column, we are on a splitter. Into our possible timelines, we add again the get all get all timelines, where we pass in a Tachyon manifold and we pass in a tuple with our new position row and a current position column minus 1. And we do again the same for the get all timelines Tachyon manifold, and we do the same for new position row and current position column plus 1. So now we'll be here. This function is basically checking individual positions instead of doing them in sync until we reach the end. So that's why we have this breaking condition. If that's not possible, we just do possible journeys, possible timelines. Why am I always saying journeys? Damn. Possible timelines. We get all timelines of a Tachyon manifold, and here we just pass in a new position row, and we don't change anything, current position column, and we just return all possible timelines. Now we can go total timelines equals part 2 Tachyon manifold, and we pass in a starting position, which is already a tuple by itself, and we can just do part 2 total timelines. Let's run this for example first. Oh, okay, what is the issue here? Why is that not working? Tuple indices must be integers or slices. I misread the error and I see a grave mistake I made here. This is supposed to be like this. And now we get 40, which is the correct answer for the example input. And now if you would run it for our own input, we will get this extremely large number, which is the correct answer for my input at least. This was by far, for me at least, the most quote unquote complex task out of all the other days. Uh, I wouldn't consider it too difficult. It's just I guess it all comes down to how you sort the visualization or solving inside your own head. I managed to solve part one pretty fast in like 5 minutes. Part two took me a bit of a trial and error because I wasn't again. It really surprised me how simpler it was. We don't have to like go for each individual position. We can just pass it like this. Um, so that's what I was trying to reuse this same logic, but after like the 20 or so minutes, I managed to do the part two. So yeah, it was pretty fun, and I hope you guys have enjoyed and have learned something, of course. Any feedback is appreciated. Enjoy your day, and until tomorrow, peace.